So to give a simple example, you're trying to say, predict the age of the captain as a function of the length of his boat. And you have data point there, and you're going to try to fit a model. Okay, so you can fit a line, and if you do this, it's a simple linear regression. Now you can also fit a slightly more complex model. And which one of the two do you prefer? Okay, so each time people say this, I need to turn around and go to the left one. This one, so the straight line. But this one fits the data better. It's overfitting. What does that mean? Okay, so basically you're telling me that almost everybody, or maybe everybody is telling me that they prefer the model that fits the data less well. Why is this? Well, it is indeed overfitting. And the idea is that minimizing the error on the test data is not the best strategy, because this data has noise. And when we're minimizing the error, we're learning the noise. We're learning statistical properties of the noise and not of things that will generalize. And it goes back to the fact that test data is different from trained data. That's the important message. So we can fit different kind of models, and we can vary some form of model complexity. So here I'm fitting what's known as smoothing splines. So as I vary smoothing parameters, so the more I smooth, the more the model is smooth, and the less well it fits the data. Okay? And so then this is known as regularization. Regularization is preferring simpler models where the definition of simplicity or regularity is one that is application dependent, but they're general concepts of simplicity that we could discuss but offline, because they will call for mathematical reasoning on, for instance, entropy of a family of distributions. And conceptually, what we're trying to do here, when we're smoothing, we're reducing the degrees of liberty of our model. We're constraining our model. And when we're doing this, we're balancing the number of parameters that we're trying to learn with the amount of data and with the amount of information in the data. That's the important thing. And this is the core concepts of regularization. Regularization consists in decreasing the quality of fit on the trained data to push the models towards a simpler model and to generalize better, okay? So this is an instance of a very classic problem, a very classic notion in statistics, which is the bias-variance trade-off. So suppose you're throwing arrows at a target, and you need to put more energy to throw them at the upper part of the target. And this is hard, so when you put more energy, you're less precise. So when you try to shoot at the top of the target, you're being imprecise. So you're scattering arrows all over. But if you're shooting slightly less strong, you're being more precise. When you're doing this, you're doing a systematic error, right? You have a bias, you're always undershooting. But if your goal is to reduce the mean square error, it is a good thing to take this bias, okay? So bias may be a good thing if it helps reducing the variance, and regularization is bias. How do we measure all this? How do we convince ourselves that this model is better than this model other than by intuition? We can test it. We can test it on left out data, all right? So if I come with new data and I look at how well the model fits on the new data, what's the error on the new data, then I'll choose the model that has the smallest error. So I've fitted the model on the test data, on the trained data, sorry. I've used the trained data to minimize the error of the model, and then I'm using the test data to measure it, okay? That's an important thing. So this is, the reason this is important is that this is a way of controlling for model complexity. If the model is too complex and it has captured noise, this noise will not transfer to new data. So typically the way we do it in machine learning is we have, when we're building our model, we have a finite amount of data. We break this finite amount of data in splits that we may call folds. And then we do what's known as cross-validation, which is that we train the model on part of the data, and we test it on another part, and then we change split, and we do it again and again and again, okay? We keep splitting our data. So that's the core aspect of machine learning practice, because this is how we know that our models work well.